Hello everyone, Active Learning here. Welcome back to another video. In today's video, we're going to talk about deep learning more in depth. So if you haven't checked out my previous video already, please check it out because this video will be an addition to that video. And hopefully I fixed the mic quality, so this video should be able to sound better. So without further ado, let's jump right in. So in this video, we'll cover forward and backward propagation, and it's going to be more in depth. We covered it in the last video, but I'll be discussing it again. And we'll cover different types of loss functions, and we'll talk about the math behind gradient descent and stochastic gradient descent. It's going to be very intuitive. And we're going to talk about the chain rule of differentiation, which allows us to update weight and biases. So let's jump into the video. So remember that this is forward propagation, basically where we take our input, multiply it by the weight, sum up the input times weight. We add in bias term, take the sum and add it to the uh, input it into the activation function, and then we get our output at the end, right? So this is our forward propagation. And we get our predicted output, which is y hat. And this is actually all review for the previous video, by the way. And so we have something called a loss function here, where we're subtracting the actual value from, where we're subtracting the predicted value from the actual value. And since we're trying to minimize the differences between them, we kind of have to minimize the loss here, right? So we have to minimize this, and so we have to get it as close to 0 as possible since we're doing binary classification here. And this is pretty intuitive because the greater the loss, the more error our prediction has, right? So we try to minimize the error our prediction has. So what is a loss function? Let's discuss about this. A loss function measures how wrong the neural network's predictions are when comparing it to the expected output, which is the actual output, right? So we're comparing our model's predictions to the actual predictions to see how wrong it is. And typically, the larger the loss, the more our model needs to train to increase its accuracy, right? And this is a common and very typical loss function for regression problems. And this function is called mean square error, right? Let me get my pointer. This is actually very intuitive. So what you do is you take the predicted value minus the predicted value minus the actual value. And this is for every data point, by the way. Predicted value minus the actual value. We square that, and then we add it to our sum, and we divide it by n. So that will give us the weighted. That will give us the average of the squared of this difference, right? And you might be wondering, why are we squaring the difference between the predicted value and the actual value? Well, consider this scenario, right? We have two data points that are trying to get our neural networks to predict correctly. If the first value gives an error of 10 and the second gives an error of -10, then our average is 0, which is very bad because error equals 0 means our model is predicting perfectly, right, without any errors, right? So it's actually bad if we allow negative errors, right? So we need to have our errors to be positive, and one solution here is to use square. And you might be wondering, why aren't we using absolute value here? Well, you will see later on that it is easier to calculate the derivative of this um, than taking the absolute value, right? And there is actually a loss function with absolute value, and we'll talk about that next. But make sure that you understand this, right? And squaring it actually makes it so that the larger errors are penalized more than the smaller errors, right? So if our error is super small, like 0.2 something, right, then it's actually not going to be a large number because it will actually be very small. However, if it's like 10, for example, then we square it, it's going to be 100. So it penalizes larger values more than smaller values. And this is the mean squared error. Okay, so mean absolute error. We discussed about this, right? We're taking the absolute value here. And mean square error, right? Why do we use mean absolute error? Mean square error has its limitations since it's very sensitive to outliers, like you saw, right? If we have a large loss, then it's going to be penalized a lot more than a small loss. So it has its limitations because if we have an outlier, it's going to be very sensitive to it. And in some cases, that might be good, but for example, for stock prediction, that might be good, but you don't want your model to be skewed by outliers, such as predicting certain house prices, right? And then in that case, mean absolute error is actually better since it's less sensitive to outliers. And this formula is pretty much the same, except that we take the absolute value instead of the square, right? Okay, and the next one is cross entropy. And this one, you'll pretty much see it everywhere for classification problems for neural networks training because it quantifies the difference between two probability distributions, right? So we're comparing the true distribution to our predicted distribution of our model to determine how close our predicted distribution is to the true distribution, right? And this is a very similar, simple formula for calculating it. We're taking the predicted value, multiplying it by um, the probability, right? Um, so this is the predicted value, for example, 0.2, and the true value is 0, right? So we're taking the log of 0, multiplying it by 0.2. And we take the sum of that, and then we make it negative, right? Again, in this case, for this example, we'll take uh, our predicted distribution 0.2 times log 0. We add it, okay? And then we take predicted for dog 0.3 and then multiply it by the true, which is 1 log 1, and then we add it, right? And then after we get the sum of that, then we make it negative, okay? So that's pretty simple. And since we're done with forward propagation, let's move on to backward propagation, okay? So let's see the weight updation formula. And you might be wondering, whoa, what is this? This is so confusing, right? So W new is the new weight. W old is the current weight the current weight we have. Let's call it W old. And this thing here, this symbol, this Greek symbol here means the learning rate, right? I will talk about what learning rate is, so don't worry about it. And this here, you don't have to worry about this. I will also talk about this, right? So the learning rate basically determines how long a training time should be, right? And also the precision of the new weight, right? The precision of your model, right? So a smaller learning rate would indicate a longer training time because every time you're subtracting by a very small amount, so it's going to take a long time to find the optimum value, right? And a large learning rate could indicate a shorter training time for loss of precision, and there's typically a trade-off for this, right? And for default, it's mostly 0.001. Sometimes you might try 0.01. And it's just a lot of experimenting. So you don't have to worry about learning rate. It's very simple. Okay, so let's go more in depth and talk about what this formula actually is, right? So let's first look at this. What is this thing here, right? In simple terms, this thing basically calculates the slope, right? You don't have to worry about not knowing partial derivatives for this. Just know that this thing calculates the slope. So let's see our graph here, right? So what do you mean by calculating the slope? So for the x-axis, we have the weight, and y-axis, we have the loss, right? So we're plotting um, the graph for this. And let's say we start at a random point here, this green circle here, and we're trying to reach this red circle. Why? Well, for this way, our loss is minimized. So we want to reach this red circle. This is the best weight that we can possibly have, right? So we try to reach this point. And so how do we do that? Well, we calculate the slope at this tangent point, right? We calculate the slope here. And this is how we calculate the slope, right? We're taking the partial derivative of the loss with respect to um, WO, right? So we're taking um, WO here is the current point we have, okay? And so we're taking this, right? And since the slope is negative, you see how it's negative? Then the new weight will be added on to the older weight, right? Because negative negative that's positive, so it'll be learning rate times the slope, which is we add that to the old weight. Now we will be getting a new weight that's further to the right of this current weight, right? Yeah. Okay. So this means that W new is greater than WO, right? Since it's plus and the slope is negative. So it's going to be plus, adding on. Okay. Now let's see it more in depth. So what you might notice is that at first, if the slope is very large, then the new weight might be a lot ahead of the old weight, right? But as the slope gets less steep, the learning rate is constant here. And as the slope gets less steep, um, we might be seeing less when we add to the older weight, right? We might be seeing less value here when we add it to the older weight. So it'll be a slower descent, as you can say. And eventually it will reach this point. And how do we know when we reach that point? Um, when the slope here is basically zero, right? When it's zero, that means we reach the point, right? Okay. And yeah, so as the slope becomes less steep, the change between the old learning rate and the new learning rate decreases. So let's see the bias update formula, right? Remember bias, we add that to the weighted sum of our inputs, right? And this is basically the same as our weight updation formula, right? This is the exact same, for this graph, instead of loss here, instead of weight here, we're just replacing it with bias. This is the exact same thing. We're doing the exact same process here, right? And more on learning rate, right? Like I said, it's going to be a lot of experimenting, but luckily there are a lot of built-in functions in TensorFlow that can help us with this experimentation process. And I will talk about that in a future video, but for now, just know that you can start the learning rate at 0.01, and then you can go down to 0.001, 0.003, and so on, right? The lower you set your learning rate, the more guarantee that you will descend to the minimum error. And that's assuming that if you train for a very, very, very long time, right? And since we don't have infinite time, we might want to start at 0.01, which is a large value, actually. And then we go from there, right? So there's a trade-off between, training time and precision here. Okay, now what if we start at this point and we reach this and then we assume that this is our minimum value even though it should be that, right? Let's say our starting point is here and we reach that instead of this, and that's very bad, right? We don't want that to happen. And this is something called the local minimum. And this point is called the global minimum. So what's the difference? Well, the local minima is basically the lowest point of this sort of mountain here, as you can say, the minimum point here. And that's not the global, the the minimum of the entire graph, right? It's only for this part. And that's an issue, right? Because for this way, our loss is not the minimum it can be, right? So that's an issue we can face. So how do we solve that, right? We could be reaching the local minimum. That's where we introduce stochastic gradient descent. And stochastic is just a fancy word for random, if you didn't know. Um, so how does stochastic gradient descent work? Basically, we start at random points, right? And for each random point, we're calculating the gradient descent for that, right? And for this, we reach the global minima. And we might have a random point here, and we calculate that, and we also reach the global minima, right? So stochastic gradient descent basically randomly selects data points, go through the gradient descent one data point at a time, and it will find all the local minima. So in this case, this is actually also a local minima since it's the lowest point of this mountain here. And we take the lowest value of all the local minima, which will give us the global minima here, right? Okay. And there are a lot of variations of gradient descent, such as Nesterov accelerated gradient, RMS prop, Adagrad. Um, I would definitely discuss these in my future videos, but for now, you don't have to worry about them since this is still pretty introductory. Now let's move on to the chain rule of differentiation, right? This is pretty important because how do we actually calculate this, right? Um, okay, so this is just our simple perceptron, right? So for example, if we wanted to calculate the weight here, if we wanted to calculate the new weight here at 4 for when we update our weights, right? How do we do that? Well, this is basically for new minus the old weight, right? Doing the process of gradient descent here. And how do we actually calculate it? Well, for our old weight, what we can see is that our loss is dependent on output 2, right? Our output 2 depends on the loss. Sorry, our loss depends on output 2. So whatever output 2 is, that will affect our loss. And output 2 is affected by the old weight 4, right? So we're calculating this part, right? Output 2 is affected by output 4, by weight 4. Weight 4 affects output 2, right? So we actually follow the same steps for updating bias. So that's actually how we calculate this part, right? The slope. And this is called the chain rule of differentiation. Okay, so let's say we wanted to calculate weight 1. How do we do that? Well, we follow the same process, right? This is very long, but it's basically the same thing. We're taking the loss here and with the derivative of the loss with respect to output 2 because the loss depends on output 2 and we are multiplying by output 2 divided by um, the output 4, the derivative of output 2 with respect to output 4, right? Because output 2 depends on output 4 and then output 4 depends on output 1 and output 1 depends on the old weight here, and that's how we can calculate this. And you might notice that, oh, if these all cancel out, then I can simply just write derivative of loss with respect to output 2 times derivative of um, output 2 with respect to output 1, and we can just skip over weight 4 since it's going to cancel out anyways, and then we can just do that and then adding on with the weight 1, right? Okay. Now, what if we have a graph like this, right? How do we calculate this for using chain rule of differentiation since we have two paths that we can take, right? So what we can do is, yeah, we have two paths. Um, Whoa, this is very long, right? You might be wondering. Um, so what we can actually do is we can take this part and we add it to this second path here, right? We have two paths. We first take this path and we add it to the second path. If we wanted to calculate um, the slope of the derivative of loss with respect to the old weight one, right? That's what we would do, because we actually do the same process here. Loss is dependent on output 4 here, and then output 4 is dependent on dependent on weight 4. We're assuming this path here, and then weight 4 is dependent on output 2. Output 2 is dependent on weight output 1. I actually just skipped over output. I skipped over weight 2 since it's not necessary, as it cancels out at the end. And then I multiply by um, since output 1 is dependent on the weight 1, right? So that's what we can do. And then we do the same thing here to calculate it for this path, right? And we sum them up to get the derivative of the loss with respect to the old weight 1, right? So yeah, that was relatively short. I thought it would be longer, but for future videos, I'll be discussing more topics for sure. Um, so yeah, in this video, we have covered forward and backward propagation more in depth. We talked about different loss functions, MSE, MAE, cross entropy, right? We discussed the math behind gradient descent, right? W nu equal WO minus learning rate times the slope, right? And we discussed stochastic gradient descent, right? Remember, we're selecting random data points, applying gradient descent to all of those data points, and we're finding um, the minimum local minima there, right? And then we just learned about the chain rule of differentiation, weight and bias updation, and yeah, I actually added an additional loss function here for some reason. But yeah, that's all for this video. And if you guys have any suggestions for my future videos, I'll gladly accept them. And if you are still confused about a specific concept that we talked about in this video, um, I'll be glad to clarify them, right? So please ask any questions or give any feedbacks in the comments below. And yeah, that's it for this video. Thank you guys for watching and see you guys next time.